This video will explore earthquakes. The learning intentions of the lesson will be explored and explained in detail on the next slide. In today's lesson, we will identify and explain passive plate boundaries, as well as comparing these plate boundaries with constructive and destructive plate boundaries. We will then name, define, and explain the key terms and concepts associated with earthquakes, including the key features of earthquakes and the different devices used to measure earthquakes. And we will then explore a labeled diagram of an earthquake, which could be used in exam or assessment scenarios. Earthquakes occur at certain plate boundaries, so commonly they would occur at passive plate boundaries where plates are sliding past one another, which will be explored in further detail in the next slides. However, in the two images shown here, we can see the breakdown of the plates on the Earth's surface as well as the boundaries between these plates. So on the first image, we can see the breakdown of all the plates. As you can see, they're outlined with a black line on each, and you can also see arrows, so red arrows indicating whether the plates are sliding past one another, colliding with one another, or pulling apart from one another. Similarly, on the second image shown here, we can see the outline of all the plates again. So the red lines indicate the outline of each plate, and it is at these red lines where the boundaries would occur, because the boundaries are the areas between the plates where action is occurring. So either plates are sliding past each other, colliding, or pulling apart, etc. So these two images show a breakdown of the ways in which the plates are broken up, as well as the boundaries which exist between the plates and the movement of the plates at each of these boundaries. Destructive plate boundaries have previously been explored in other lessons. However, today we are going to do a quick review of destructive plate boundaries before beginning to study passive plate boundaries in detail. So when plates collide, the crust is destroyed. As previously explored, when an oceanic plate collides with a continental plate, the oceanic plate, because it is heavier, will subduct into the mantle. This will cause the continental plate to buckle. This can lead to the formation of fold mountains or volcanoes, as seen here in the second image, where we can see magma entering up into the crust, where it can lead to the formation of volcanoes, as well as the eruption of a volcano in the form of lava. Again, constructive plate boundaries have already been explored in previous lessons. However, we will do a quick review. As two plates separate, magma does swell up to fill the space between the two plates, which can actually lead to the formation of new solid crust as the magma cools when it hits the seawater. This can lead to the formation of volcanic islands, volcanic mountains, or mid-ocean ridges, as seen here in the second image, where we see the formation of a mid-oceanic ridge between the two plates which are actually separating. Passive plate boundaries occur in areas where plates slide past each other rather than colliding with one another or pulling apart from one another, as has previously been explored with other plate boundaries. As seen here in the first image, the red dot shown shows the point where the plates are actually sliding past one another and friction is starting to build up. As plates slide past each other, their edges can become locked together. This can lead to the buildup of pressure, which continues to build up more and more gradually over time. This eventually leads to one of the plates snapping or jolting forward suddenly, which actually leads to a great release of pressure, causing the earth to tremble in a series of earthquakes. And as seen here in the second image, we can see where the earthquakes are occurring between the plates at the exact point where the plates are sliding past one another. We will now explore the different features of an earthquake and the key terms associated with earthquakes, including the different ways in which earthquakes can be measured. As seen here in the image, the focus point of an earthquake is the point deep within the Earth's crust, where the earthquake begins beneath the surface. So this is the point deep down within the crust where the earthquake actually originates, which may be the point where plates are actually sliding past one another and the pressure is building up. As seen in the image here, the epicenter is the point directly above the focus of the earthquake that is actually on the Earth's surface. The strength of the earthquake is greatest here, considering this point is directly above the focus, and so this would be the area where pressure will be felt the greatest. The shock waves are a form of pressure felt from the earthquake, both beneath and on the surface, as they spread out in circles from the focus point of the earthquake. As seen here, the effects on the surface can vary greatly. So locations nearest to the epicenter will suffer the most damage, as the crust will feel the greatest amount of pressure and trembling at this point due to its proximity to the origin of the earthquake. As seen in the image here, the point nearest the epicenter, you can see major damage with the buildings, and there would also be major damage with roads, etc. And then you can see at further away from the epicenter, there will be minor damage. So buildings may not even collapse. The shock waves, as seen originating out from the focus point in the epicenter, may not even be felt to a very strong degree at this point, and so the trembling of the Earth's crust may not be extreme enough to cause damage, so damage will be minor compared to the damage felt in locations very, very near the epicenter. The different ways in which earthquakes are measured and recorded will now be explored in detail. A seismograph is an instrument used to measure and record an earthquake and to record how long the earthquake lasted. As seen in the image here, this is an example of a real-life seismograph which could be used to measure actual earthquakes. So a type of a pen would record the data on the form of paper seen here in the picture, and it would record lines which would be an indicator whether or not an earthquake was occurring. So if there was very little movement, that would indicate that there was no movement of the crust. However, if there was a lot of movement of the pen, this would indicate that there was a lot of movement on the crust, as well as indicating how long the earthquake was actually lasting for and the strength of the earthquake based on how much the pen actually moves over time. The image shown here actually portrays evidence of an earthquake from a seismograph. As we can see, the first section of the image where the lines are red, there's very little movement with the seismograph, which would imply that there was very little trembling or movement of the Earth's crust. However, as we see, as the image moves over towards the right, where the lines appear green, we can see that there is lots of squiggly lines, which would imply that there was a lot of movement and trembling on the Earth's crust for a period of time. The image shown here shows an example of the Richter scale. This was the original scale used to measure the magnitude or strength of an earthquake. The numbers are assigned to earthquakes based on the strength of the earthquake. For example, if an earthquake was measured at 1 on the Richter scale, that would actually imply that it was very small. Those kind of earthquakes are actually very common, might even occur daily, may not even be felt in some areas because they're so small and almost irrelevant, and they may not cause any damage or very, very little damage. However, if you were to go to 7 or 8 on the Richter scale, that would imply that there was a lot of damage, that the earthquake was quite major, that it would have definitely been felt in certain areas, there could have been a lot of damage, maybe even death, and that these earthquakes would not be as common as smaller earthquakes, as they will be quite major with movement of the crust significantly bigger than that of 1 or 2 on the Richter scale. Also, on this scale, each number is 10 times stronger than the previous, which would imply that there's actually quite a difference between each number as you go up and up and up, which would actually suggest that the higher up numbers would signify a very, very strong earthquake. The images shown here could be used as examples to show a large-scale earthquake, so maybe an earthquake which measured very high on the Richter scale or would have been quite significant on the seismograph. So as you can see, it can lead to a lot of damage on large-scale earthquakes. So there could be the collapsing of buildings, damage to roads, damage on streets, such as signposts or lights on the street or traffic lights. This could also lead to death of individuals if anything was to collapse or fall while anybody was near, and obviously a major trembling of the crust. The diagram shown here on this slide is a very good example of a label diagram which could be used to provide a successful diagram in an exam or assessment scenario if asked to provide one of an earthquake. So it would not necessarily have to be drawn in 3D form as the diagram on this slide is. However, the different labels on this diagram are very good indicators of where you could draw labels on your own diagram. So if you were to imply where the crust is and where the focus point would be down deep within the crust, how the epicenter would be directly above this on the surface, you could show your seismic waves or shock waves. So seismic waves is just another way of saying shock waves. You could draw those to show how far out the earthquake was actually felt, so how far out the trembling of the earthquake would actually be felt on the surface. You could even show damage on the surface if you wanted to show maybe trees, buildings or roads which were damaged or collapsed, etc. And you could even indicate the type of plate boundary which caused the earthquake. So in this image they are showing that a passive plate boundary caused the earthquake, and you can see the point where the focus point is where the two plates are sliding past each other and pressure is building up. So if you wanted to indicate the plates in your diagram, that would also be very good and would add to the diagram if you wanted to include that detail. So to conclude our lesson, we will just explore whether or not we have met all of our learning intentions. So we have discussed passive plate boundaries, and we have compared them with constructive and destructive plate boundaries and the different occurrences which would happen at each plate boundary. We've explored key terms associated with the earthquake as well as the ways in which the earthquake is measured, and we have explored a label diagram of an earthquake with emphasis on each label and where it would be appropriate on the diagram.